Hello students, welcome once again to functional analysis revision. This is the next video on functional analysis. So let us start with this. Okay, so today what we are going to do is this. Okay, point number 10. We had done till 9 points. This is point number 10. Let's say L of P, LP is equal to X is equal to, okay students, so X is equal to, okay, the Greek letter Z, okay, that is this is a sequence, okay, Z of I. All right, now this Z belongs to, Z of I belongs to F, okay, for all I belonging to natural number, okay, and you should also know that summation of I starting from 1 to n, okay, mod Ci of P is less than infinity. Very important point, this one, okay, very important point. Now what happens is we define the norm of P. How we are going to define the norm of P? That is L of P, okay, tending to the real numbers, okay, by norm of X of P, okay, which is equal to, this is equal to, all right, you can write there, equal to starting from summation of I starting from 1 to n, all right, norm mod of Zi of P whole to the power 1 by P, right, for all X is equal to Zn sequence, okay, that is what when P is greater than equal to 1 but less than infinity. Then if this happens, then that LP, then LP comma norm of P is a normed space. Normed space, of course you know normed space is shown this way, normed space, okay, and it's also a Banach space, is also a Banach space. All right students, that's your point number 10, okay. Now we further move on to point number 11, okay. So let's move on to point number 11. So point number 11, you have L to the power infinity, okay. When you have that is the Z of n is a sequence, okay, such that Zn belongs to F, okay, comma, for all n belonging to capital N, okay, comma, then Zn function is sequence is bounded, okay. So let's define it now. Now defining the norm of infinity, L infinity moving to real numbers by defining it by norm infinity is equal to the supremum, okay, supremum of course j greater than equal to 1, right, but less than infinity, supremum of zi, okay, the x will belong to L of infinity, okay. Then norm infinity is a norm on L to the power infinity. It's also a Banach space. It's also a Banach space. Then the norm is a Banach space only, okay, then norm some set C a comma b in the interval a comma b belongs going to R by, we can define it by norm of x is equal to integration of a to b, okay, mod x of t dt, okay. So this is done, and you notice this, actually this is the 12th point, or you will have this in the next point, okay. You can write this in the next point. This is happening when you have your C going from A to B. C is given is a subspace, okay, of all continuous function on the closed interval a comma b. Then we can define this, okay, we can define this, you can mark this as point number 12, doesn't matter. Then you can define that, okay, but the norm is a norm, it is a norm, but it is not, but on it is a norm on C, no doubt about that, okay, a comma b, but it's not a Banach space, but it's not a Banach space. Alright students, so that's it for this part, okay. We shall continue with this in the next part. So thank you for watching. See you in the next video. Bye bye.